state estimation and discrete time linear dynamic system. Although before that there is a chapter, but that's not that much important because we are interested for discrete time system. So before this there is a chapter for continuous time linear dynamic system, but continuous time system is not that much in used for the applications. We used discrete time system for state estimation and tracking purpose. So we are only taking this chapter and will study about the estimation algorithm for a discrete time linear dynamic system. Remember the notation. Okay, means this cap is known. We denote this cap when we apply estimation. Means this denote estimate. The bar sign. This is not minus. This is bar sign like x bar. Okay. This denotes the prediction. Okay. And suppose this is time scale, and here is k time, and here is k plus 1 time. Then x of k is the result of the estimate in current scan. Okay. This k is current scan. This k shows that sk is conditioned on zk. Means the value of xk is estimated using the measurement, sensor measurement receiving in k scan. Okay. So this is, we can say, updated or the state estimate, and then we have to propagate. We have to send this information to the next scan. Okay, so when this value is transformed or transit, this value is transit from this side to this side, then here is the notation of x, right? K plus 1, like this one. And what this means, this k plus 1 means that it is obtained from here. This state estimate is sent to or transit to another time, and this time is this information said that this is coming from the previous scan. Okay, so you can see in some paper, some people shown here that k minus 1. Okay, but for your understanding, we are saying that we are propagating or transiting this information to another side. So this is like k plus 1, k plus 1. Okay. So and now we are updating this x of k plus 1 with conditioning of k, means current scan measurement. So we say that this is a prediction. Okay, in this notation, k plus 1, this bracket means, this condition means this, we are calculating this value given k. We are calculating this value given the k measurement. Okay, and this bracket means we are calculating this value using using this measurement. Okay, so these are few notation. Now derivation of estimation algorithm. Okay, so first we must know the model. We must know the model of target and sensor. Okay, so target model and sensor model already given in this slide. Okay, so suppose x of k plus 1, f of k, x of k plus g of k, u of k plus, and this v of k. Okay, here we already discussed last week that this must be known. Okay, suppose initial time is known, and suppose this is any value. True value, because if it is known, then we can generate some next time state of the object. Okay, this is current state which must be assumed to be known, and g of k is constant, and this is control input, and this is noise, Gaussian noise, and normalize having a zero mean and variance square. Okay, so if this is known, then we can calculate the next time state like this, and where k is a number of scan, k is 0, 1. Okay, and you know another thing is a sensor model. Sensor model is h k plus this is sensor model. Okay, now we have given this model. Okay, and how to solve this problem of estimation algorithm? There are one is the prediction state. Okay, state prediction state. This is state prediction state, and measurement prediction state, and finally estimate state, state estimate state. 3 steps. Okay, so number 1, the state prediction state. This follows from this equation. Okay, and this is used to generate the trajectory of the object. The target trajectory is generated by this one, and this is sensor model which receive the measurement information from the object. having this noise and this noise. This is sensor measurement noise, and this is the target noise. So it follows, the prediction step follows by applying the prediction equation with expectation. Apply expectation condition on zk. Okay, two equation, one. Okay, so k plus 1 condition on zk equals to expectation over this equation, right hand side, f of k and xk plus g of k and u of k plus v of k and condition of zk. Okay, now this is equals to, if we solve the expression, then this is the estimate value condition of k. Okay, because this conditioning means this value is condition on the measurement zk. Okay, this is equal to this one. This means the expectation or mean value of this one. This is the mean value of this one, equals to f of k remains same, is constant, and expectation, this is also the mean, and then g of k remains same, constant, e of k remains same, and expectation over this, because this is a variance having the zero mean and variance square, this will become the 0. Okay, expression of v of k condition of zk is 0. Okay, because it is Gaussian normalized with 0 mean and variance square. So this is your state prediction formula. And what about covariance? For covariance, you have to subtract this equation from this one. Subtract the above equation from 1. Above equation 3 from 1, we get x of k equals to f of k and plus v of k. Okay, here we subtract this equation, this, so this is the difference between this thing and this thing. Okay, this thing is the difference between the minus. Okay, this is the difference between, we have subtract above equation from this one. This is the difference. This notation is estimation error. Okay, this is the difference between this equation and this equation. And again, fk is a constant which is multiplied with this one. So we can take a common f of k. F of k is have been taken common, and again difference between the x of k and this one is this thing. Okay, and and this thing is cancelled, this minus cancel, and remaining part this will come as it here stands. Okay, if we subtract this equation from this one, then this obtained. So this is called the state prediction error. Okay, clear? Now the state covariance obtained from by taking the expectation over this equation. So state covariance expectation above equation. Okay, now expectation of state covariance. This is for covariance. So we have to take the transpose of the error, and one same, one have a transpose. So this is SK expression of transpose condition of ZK FK transpose and V of K transpose. We are taking here transpose because we are calculating the covariance, expression of covariance, okay, of K plus 1, this thing. So here why we take the transpose or F, because this X is orthogonal, this case is orthogonal. If we do not apply this thing, then this cannot be calculated because of dimension mismatch. So this vector is orthogonal matrix, so we have to multiply this transpose with this one, so that we can easily calculate the state covariance of the X. So what is the result of this one? This is, we have already denote this thing as a covariance like P. Okay, we have denote the covariance with P and the state with X. This is the state and this is state covariance. So this is your P K plus 1 okay. So again this is P, but this time this K is condition is the current K, and this is FK transpose, and this thing is equals to Q. Again this is the covariance of the noise, as we have discussed that this is covariance of the state okay. here. This is the target plant noise, or you can say target model noise. So target model noise is denoted by the V, okay, V, and the expectation over this one is the covariance, okay. Expectation over this one is the covariance. We said that this is Gaussian normalized having zero mean and the non-covariance like Q. Okay, so this is the white Gaussian noise which is normalized with the zero mean and non-covariance Q. So this is Q is the expectation over Vk transport. Okay. Now the predictive measurement. This is second step. Okay, the predictive measurement, for the calculation of this measurement, you must know this value. Okay, so from sensor equation this one, and it follows similarly by taking expected value of equation number this one, conditioning on, we have take the expectation, okay, condition on zk, and so therefore zk plus 1 is z, and condition of zk, expectation of hk plus 1. This is because this is already we know, okay. So for the next time scan, we have to put the k plus 1 and then k plus 1, because we have already calculated this value k plus 1, okay, because we use this information and update by applying expectation. Now this information is updated, or this information used to calculate the mean value for the object state at time k plus 1. So this is inputted here, k plus 1, this is expression over a whole bracket. So this is the mean value of zk plus 1, condition of k, this is k plus 1, okay. And this is h k plus 1, and this is again mean k plus 1, conditioning of, because this condition of the scan k, okay, and expression over the this noise, this measurement noise is 0, okay. So this is omitted. So this is the your measurement prediction. So what it calculates, it calculates the measurement prediction condition on the scan K. Okay, if this value is known, then this value is obtained the next scan position of the object state, and we have to apply the expression to calculate the mean of this equation. This calculate the mean of this equation using the current scan. Suppose here we are one first scan. Okay, so condition on first scan, we have calculated the 1 plus 1 second scan state estimate. Then this has a state covariance like this one. Now this information is sent to here. Here is x of 2, conditioning of 1, because this calculated based on this equation, and now this is used to calculate the measurement prediction. Okay, and similarly this is the measurement prediction for the 2 condition on K, 2 condition on scan 1. Okay, now it has also the covariance. So for finding the covariance, we must first calculate the measurement prediction error. This is measurement prediction error by subtracting above equation and from this one, from 2 above equation from 2. So if we minus this thing to this thing, this will be denoted by, so this is similar way like here. So this is the same way that minus and this is equal to k, h of k plus 1, and this thing k plus 1, k plus w, because here is not w but here is w, wk plus 1. We put here k plus 1 because we are finding the next scan prediction. So for covariance of this prediction error, we must apply the expectation over this equation. So if you apply the expectation, like this, conditioning on zk, so this will like we said p z z. We denote the covariance of this object by p z z, which means in Kalman filter we denote this thing with the s, k plus 1. Okay, this is not like this p. Okay, this covariance of is a state covariance. This p is for z z. This p is for the covariance of the measurement and the state. This is covariance between the measurement prediction and the state prediction. So this covariance and this covariance is different. Okay, so and this means that the covariance of zk plus 1 condition of zk. Okay, so this means the covariance of zk plus 1, conditioning of zk. Okay, and how to obtain this? This means that we have to find the k plus 1 k plus 1 transpose like this, like the similar way here. Here we have taken the expression for the covariance of x. Now the expression for the covariance of the z. So here, if we apply the expression over this one like this, k plus 1 and k plus 1 transpose h of k plus 1 expression x k plus 1 k plus 1 transpose, and this conditioning on zk and expression over this one w k plus 1 and w k plus 1 transpose. So again this is equals to, again this thing is Gaussian white noise, which is normalized with a zero mean and covariance R. So R is a sensor measurement noise. Okay. So this is R of k plus 1. Okay. And this thing is sk plus 1. Okay. And this thing is k plus 1, pk k plus 1. Okay. This means that this is the expression or the mean value of the covariance of the object state, and this is rk and this sk. So your covariance of the measurement prediction is equals to sk plus 1 equals to h of k plus 1 and pk plus 1 and h transpose k plus 1 So this is the equation 6. Okay, clear? First you have to obtain the mean value of this one, then covariance of this one, then this is used for the measurement prediction here, then again you have to calculate the covariance of this thing, and this is used as a filter covariance. Now we have final step, the estimate update or estimate state. State estimate. So before this we have to calculate the one more thing, that is the filter gain, and filter gain is obtained by calculating the covariance between the state and the measurement. So we have to first calculate the P xz and PZZ. Okay, PZZ we have already calculated here. PZZ is your covariance between the state and the measurement prediction. Now we have to calculate this thing. Okay, so this whole thing is the filter gain. So what is Pxz? Similarly, it's a cross covariance. This is a cross covariance of the x and z. Similarly, we replace. We have to take the expectation over the x and expectation over the z. And as this is the covariance, so we use this notation. Like this, expectation x k plus 1 and z k plus 1 transpose, because this is cross covariance, so we have take this thing and this thing transpose, and condition on zk. Okay, so we have to put the value of this thing in this equation. Zk, our zk is equals to this value. Okay, our zk is equals to this value. So this value same. This value is same. So we have to put this value h of a plus 1 and x a plus 1 and w a plus 1. Oh, this bracket and this bracket. Now we have to multiply this thing, okay, and here is transpose, here transpose, this transpose, and conditioning on zk. Now we have to multiply this thing, as transpose is a whole transpose, so here is also transpose, here is also transpose, and here also transpose. So if we multiply inside terms, then this multiply with the transpose of this state, okay, and this thing is equals to k plus 1, because your p of k plus 1 condition of k is equals to this thing and transpose of this thing. Okay, if we multiply, so this is also transpose, this is transpose, and this is transpose, but the expectation of this thing multiplied with the transpose of this guy is equals to the pk plus 1, and the remaining part is multiplied with this one, h k plus 1 transpose, okay, and this thing is multiplied with this one, but the expected value of this thing is 0. So 0 is multiplied with this thing, it will become a 0. Okay, 0. So now your PZZ, BXZ in this equation. So this is multiplied with PZZ. PZZ, this is multiplied, this is the inverse. Okay, this is inverse. This thing is multiplied by the PZZ, and your PZZ is this one. This is the PZZ. So your PXZ and PZZ inverse is equals to this guy, and we denote this value like W, capital W, K plus 1, and this guy, K plus 1, and H of K plus 1. This thing is the PXZ, and multiplied by this thing S K plus 1. Here is a minus inverse, here inverse. So this is your filter gain. Okay, clear? Now you have the final step. This is the final step, the update equation. So does the updated state estimate. Okay, you can see in the slide we have already denoted this estimate like this one. So this denote the state estimate. So what we are estimating? We are estimating this guy, K plus 1. K plus 1. We already know x of k. Okay. After calculating the measurement prediction, we are estimating x of k plus 1. The estimate value of k plus 1. This value is called the filtered value. Filtered value. Okay. Now this we have to send this information, update. We are going to update this information based on k plus 1, condition of k plus 1. Okay, this equation, this conditioning means the measurement is given to you from k to k plus 1. Okay, from k to k plus 1, because for update or transition from one place to other place, you must know the other place value, otherwise you cannot go to other side. Okay, so this information means the measurement is conditioning on k plus 1, and this is value is for k plus 1. So you must know the k plus 1, otherwise you cannot transform the x of k to k plus 1. So we have to take the expectation of x of k plus 1, condition of j k plus 1. So this means k plus 1, that zk k plus 1 means information from zk to zk plus 1 is known, is given to you. So according to this thing, we have to calculate we have to update using this filter of gain, like this one, k plus 1, k plus 1, and this equals to how we do apply. We apply using this thing Okay, we have already know this thing, and add, we are updating, so we have to add information, addition to this thing, which gives you this thing. So this plus sign is the wk plus 1, and this thing is new, this sign is new. This is any variable you can write, and you can denote it to any other variable, k plus 1. Okay. So this is the residual measurement denoted by nu, and this is equals to the z k plus 1 minus z predicted measurement okay. So we have to multiply the filter gain to the residue, to the difference, of the predicted measurement. We have predicted the measurement for k plus 1. Okay, we have predicted measurement for the next scale measurement, conditioning of the zk. Okay, so now what is the difference? This is the sensor measurement. Okay, this is the sensor measurement. Sensor send to you this information, okay, the real data. Now we have to check the residue or difference, how far this value means this prediction is how far from zk plus 1. Okay, so other notation for this thing, as this is the stack prediction. So when you go for some research paper, this equation is denoted by, this is stack prediction. So this equation number 8 is called the stack estimate. Okay, this is the stack estimate. Okay, and this new is an innovation, is called as innovation or predictive innovation or the measurement residue. And in this view, sk plus 1 is a measurement innovation. This is called the measurement innovation, and this is called the measurement innovation covariance. Okay. Now, finally, we have calculated this thing. Now we have to calculate the covariance of this thing. So, state updated covariance pk plus 1 k plus 1 is pxx minus pxz pzz inverse pzx. So this is formula for calculating the state update covariance. Okay, so here this guy is this thing, the expected value of this thing. Okay, and this guy is this value, the cross covariance of the state and the measurement error. Okay, this is the p k plus 1 and h k plus 1 transpose, and this is your S inverse of k plus 1. Okay, and this is your cross covariance of z and x. So this is equals to the k plus 1 in a similar way. Okay, now you have to put the values. So your bk plus 1 equals to pxx minus pxz k plus 1 h of k plus 1 transpose and S inverse k plus 1, and then this guy p of k plus 1 and h of k plus 1. So take the common of pk plus 1 from here. So this is pk plus 1 is taking common. This is identity matrix because all other things are matrices, and this part 1, 2, 3. This part is your W. Okay. W k plus 1 is equals to P of k plus 1, H of k plus 1 transpose, and S of k plus 1 inverse, and this has been taken common. Now the remaining term is H of k plus 1, and okay. So here updated state covariance, equation number 8, 9. Okay, and that's all. So this equation number 9 and S inverse, there is S inverse, this equation number 6 PZZ, this equation and this equation is called the covariance of the filter. So we have done this thing on whiteboard. So as you can see that WK is a filter gain is very important. So WK, the filter gain, is proportional to the covariance of the state, covariance of the predicted state, okay, and is inversely proportional to the filter covariance. This is the filter covariance and this is the predicted state covariance, equation number 4. So this, what does it means? It means proportional to this one. If this state covariance is bigger, is larger, then this is large, and if this is large, then this filter covariance is very smaller, and this is covariance is obtained from the difference between the predictive measurement and the state prediction. Okay, this is obtained from this thing. This is the this is your predictive measurement error. That is the covariance between the measurement prediction and the state prediction. It means this is the measurement innovation. The measurement residue is smaller. If covariance of the filter is smaller, like this here, the gain is large if the state prediction is inaccurate. Means the state prediction, equation number 4, is inaccurate, having the large covariance, and the measurement is accurate, has a relatively small variance. If the measurement is accurate, then it has a small variance, and likewise the filter gain is large. Okay, because this is inversely proportional, and the filter gain is small if the state prediction is accurate, has small variance, and the measurement is inaccurate, has a relatively large variance. So we actually do not want this inaccuracy in the measurement. We do not want the inaccuracy in the measurement, because if the distance between the it's the difference between the z calculation and predicted measurement is very far, it means the target is very far from the sensor measurement. It will cause a bigger estimation error. Okay, so measurement prediction will become very large, and the gain will become very small. Okay, and the gain will become very small. So a large gain indicates the rapid response to the measurement and updating the state, while a small gain yields a slow response to the measurement. Okay, so in the frequency domain, it can be shown that these properties correspond to the higher or lower bandwidth of the filter, and a filter whose optimal gain is higher yields a less noise reduction, as one would expect from a filter. So this thing yield the filter calculated covariance, which are exact if the model assumption, that is a Gaussian modeling assumption used in the filter derivation hold. Means if your estimation algorithm obey the Gaussian assumption, then this is these calculations are exact and perfect for the filter gain. Okay. So this is an overview of the Kalman filter estimation algorithm. So this column is the evolution of the system, tracking system. This is control input, and this column is the estimation of the state and state covariance computation. Okay. So you must know your system must know the x of k at at time tk. Okay. Now transition to tk plus 1 means here the trajectory is generated. Here your algorithm generating the trajectory using this information. So using this information, the trajectory is generated for k plus 1, where v of k is a Gaussian noise entering into the system, and u of k is the control input. So u of k is a non-control input or sensor motion, okay, or any sensing point that is inputted here and here, and again this is inputted to here, measurement at t plus 1. So this is used to calculate the measurement residual. This here is the noise is entering to the measurement. The sensor noise is entering the sensor model. So the k plus 1 is this thing is calculate the measurement. So because this thing is the 2-dimensional or 3-dimensional position and 3-dimensional velocity, but this model do not need the velocity. Okay, do not need the velocity because we are calculating the measurement, position measurement. So this thing is a, suppose if a scenario is a 2-dimensional, then this is 4 by 1 vector. So this zk plus n is a 2 by 1 vector. This just select the only position information and adding the noise, measurement noise here. So this is only position noise, and then it will come here, and where the state estimate of this one is calculated by applying the expectation over this thing to calculate the mean value of this object. If you have find the mean value of the if you have find the mean value of this equation, then this is said to be the state estimate of the x of k condition on k. Okay. And now this equation is used for the prediction, state prediction. K plus 1 condition of k is equal to this equation. Okay, and similarly the it has a state covariance pkk. Okay, and now this equation will calculate the state prediction covariance k plus 1 condition of k using this equation, as we have already discussed it, by taking the expectation over the covariance of the state estimate, like this one, like the equation number 4. We have find the equation number 4, pxx. So this is the pxx covariance of the state estimate. So this will become like this one. Now the innovation covariance pxz. So now this is the pzz. Innovation covariance is pzz. So innovation covariance is the covariance of the measurement prediction and state prediction. Okay, it's the covariance of the measurement and the state prediction. So this one, and this will calculate the filter gain here. So after the measurement residual, the updated state estimate is obtained using the residual and the filter gain. And similarly, the filter gain is used to obtain the updated state covariance. Okay, clear? So this is a simple flow chart, and these notations are used everywhere in the estimation algorithm. Okay, clear? Okay, same thing is written here. Okay, same thing is written here. So your estimation cycle consists of the state and measurement prediction, time update, and state update, or the measurement update. So the state update requires the filter gain, and the covariance calculation are independent of the state measurement and the control input. So the control input is can perform offline because it is assumed to be known, and the Kalman filter has no idea for calculating the control input. Okay, so this will be calculated by the offline, and the covariance calculation are which are the W and SK plus 1. W of K plus 1 and S of K plus 1 are independent from the state and measurement covariances. Okay, so if you have any question, please ask me.